Hello everyone. Our topic is recognition of tomato leaf disease utilizing improved efficient V2 convolutional neural networks. The team members are me, J.V. Singh Rathod, Aditya Gupta, and Utkarsh Agarwal. Moving on to the abstract, Utkarsh will take on from now.
Abstract. By classifying images of healthy and diseased tomato plants into separate groups using a modified version of EvolutionNet V2, it aims to identify the diseases affecting the tomato plants. The most significant results showed the EvolutionNet V2 performed exceptionally well, obtaining a 99.9 accuracy rate, showing the possibility of utilizing CNN models to identify tomato illness. The best features of dense networks and deep residual networks are combined in this hybrid deep learning framework to decrease the number of training parameters while enhancing accuracy, information sharing, and gradient. The picture properties and hyperparameters of the input images were modified and utilized to divide the tomato dataset into groups. And
Moving on
now
to the
the
introduction.
introduction. The production of tomatoes, a significant source of income in India, is anticipated to exceed 20 million metric tons annually. Deep learning algorithms can be used to develop a trustworthy and effective automated method for early diagnosis of tomato leaf disease. Traditional detection techniques, which can be tedious and imprecise, call for visual assessment by human experts. Because of this, accurate and effective automated methods are needed for early diagnosis of tomato leaf disease. Deep learning techniques use many layers of computing to gradually extract high-level properties from raw input. Deep learning, seen from a different angle, is the computer modeling or automation of the human learning process from a source like a picture of a dog to a learning objective like a dog.
So for the literature survey, we took some research papers for our own paper, and these are based on deep learning and CNN's architecture like AlexNet, ResNet 50, and GoogleNet for identifying illnesses in tomato leaves. So now, moving on to dataset. So the dataset we are using is a plant-based dataset. And this dataset includes 11,000 RGB photos, and this dataset is separated into 10 categories, in which there are 9 categories for sick tomato leaves and 1 category for healthy leaves. Now, the full dataset is divided into a ratio of 90 is to 10 for training and validation set, with each image having a resolution of 256 cross 256 pixels. Now, the 9 illnesses that are included in the dataset are bacterial spot, early blight, late blight, leaf mold, septoria leaf spot, two-spotted spider mite, target spot, tomato mosaic virus, and tomato yellow leaf curl virus. We have used different orientations, sizes, lighting conditions, scaling factors, textures, and patterns to enhance each individual feature. So this study will focus on specific plant diseases related to tomatoes, and we'll see how well our proposed work will work, and we will later do a full evaluation of our proposed task. Now moving on to proposed methodology.
Yeah, moving on to the proposed methodology. Using the Jira Python library, the data was used to train the model was taken straight from the source. We use the hyperactive library, offering values for hyperparameters that maximize the model's productive accuracy for quick prototyping CNN model. And using Jira Python library, the hyperactive library, the NumPy to perform mathematical and logical operations on arrays, and the implementations for data augmentation, which was a technique for quickly creating a CNN model. And to avoid overfitting and data augmentation, generates training images using a variety of processing methods while also increasing the amount of images. The head convolutional layer and the transfer learning method are used by the efficient V2 model to take the outputs of the work done by the preceding layers and do something meaningful with them. A global pool averaging layer, a fully linked layer, and a softmax layer are used to place the picture into one of many categories. To achieve a smooth dimensionality reduction and improve the training process, batch normalization and dropout layers are also used. The range of parameters in a particular characterization map is narrowed by a normalized linear unit ReLU, a non-linear activation function, and effective connectivity and data handling depends on suggested efficient V2 characteristics and pooling techniques. A 1x1 convolutional layer, the bottleneck layer, as we say, is thought to reduce the number of parameters determined at each level before a bigger kernel convolutional filter is employed. The performance is further improved by the ReLU non-binary activation function and the 11 convolutional layers used, which further deepens the network. The pooling layer reducing the need for parameters while replacing entirely linked layers with subpar ones, resulting in an 11% increase in training size. The suggested model incorporates significant changes, including regularization, label smoothing to alleviate a representational bottleneck using the Adam optimizer, offering the feature bank of a more thorough and expansive module, normalizing the auxiliary classifiers, fully linked layer, and more. The proposed model makes the following significant changes despite the fact that the present efficient V2 uses categorized convolutional, smaller convolutionals, asymmetric convolutionals, and auxiliary classifier, replacing the RMS prop optimizer with the Adam optimizer, which combines the advantage of the stochastic gradient SGDM as shown as the root mean square of propagation RMS prop optimizer. A representation bottleneck can be eased by a more complete and broad modules feature bank, and as a result, information loss will be prevented. Batch normalization, the fully linked layer of the auxiliary classifier. Label smoothing regularization is a technique basically for improving a classifier by estimating the effect of label dropouts during training, which stops the classifier from overfitting and producing false positive predictions. Label mappings, also for training and testing, are 1:1. The process of mapping from the source to the intended destination is another name for it. And this is a comparative analysis on the several DL designs in terms of layer count and parameters. And moving on to the results, Aditya.
Yes, Javier. So moving on to results. So our new network uses inception layers and forward learning to train with minimal input data. So we are using here a transfer learning, which greatly improves generalization in another task by using information from a prior assignment. So the last layers are replaced with new layers like the linked layer and the softmax classifier. So now talking about the parameter value of the parameters that we have set for the model. The training period is set to 100 iterations, at which the point of accuracy of model is checked. The default batch size of 32 means that 32 values will be processed simultaneously at one time, and the network uses a dropout layer with a factor of 0.5 over 3 layers. And during the backpass, weights are not updated, and activation of downstream neurons is repressed at a regular interval of 50 epochs. Maximum learning rate of the network is increased by this fault factor at this time of year. And CNNs are trained using an Adam algorithm and adjustment weights with a batch size of 128 for each iteration. Padding is also performed throughout the sequence regularly, and L2 regularization is set to 0.0001, and the proposed design model's training error is diminished. The experiment's average training and testing accuracy is found to be 99% and 0.017 loss, and the proposed model outperforms efficient V3 model by 0.84 and 0.8%. So these are the values of the parameters that I just said to you. Now this is the sample result of the overall head. So for the for uh, our proposed network has the best accuracy in identifying the septorial leaf spot, and for the other and also the early blight spot, and for the remaining diseases it also also finds the other diseases well, but it has the higher accuracy for septoral leaf spot and early blight disease. Now we will compare the performance of our proposed network with other various deep learning architectures. So if you can see the graph, our proposed architecture has the highest accuracy amongst all other DL architectures. Also, we have the minimum loss of 0.017, which is very less if you see among all the DL architectures. The average time per report taken by our proposed network is 865 seconds. So if you consider all the parameters, our proposed network is better than all the other DL architectures. The training accuracy and testing accuracy is found to be 99%, and the loss is found to be 0.017. Now moving on to conclusion.
So this paper presents an enhanced version of the EfficientNet V2 model for disease identification in tomato leaves. To achieve better performance with fewer parameters, the suggested method uses a transfer learning technique generated from a modified version of EfficientNet V2 on the tomato dataset, and test the proposed model, which divided the tomato dataset into 90 and 10 subgroups, had a 99.2% accuracy rate. The suggested deep learning model outperforms the state of the art by a mean of 6% in terms of prediction and accuracy. Insufficient dataset, less than ideal resilience, symptom fluctuations, image spectrum variations, and modifying the model's hyperparameters can all be addressed with the use of transfer learning and data augmentation techniques. This environment is ideal for investigating and applying DL approaches to all the classification of plant diseases. And to show this, this is a code which at the starting shows the how the data set is being taken, downloaded through it, and this showing the uploading of the data set to the model. Moving on to the feature selection and extraction of the images. And this is the train generator. And this is for the validation generator. And this is here where we have applied a model showing that we have used EfficientNet V2 and these different layers for a code for a model, and these different callback values and different matrix and optimize and Adam optimizer. And then these are the various epochs used, and these are the various parameters and the total parameters and the trainable and non-trainable parameters we got. And moving on to the result, this is a final result for which we got 99.2% accuracy, and this is the model loss. So thank you for seeing this. Thank you.